Hello my dear students, welcome back to your channel. Hope you all are doing well. Today I am going to start one short revision of chapter Magnetic Effects of Electric Current of class 10 science. In this chapter, different topics to be covered are first, what do you mean by magnet, then magnetic field and magnetic field lines, their properties or state observation, then magnetic field due to a straight current conductor due to a circular coil, then magnetic field due to a solenoid, after that force on a current carrying conductor, at last electric motor, and then last topic of this chapter is electromagnetic induction. So I will cover each topic one by one. Let us start this chapter. What do you mean by this chapter? Magnetic effects of electric current. It means what is the magnetic effect due to electric current, how electricity and magnetism are related to each other. But before starting this chapter, you must know about magnet. What is magnet? You know, any substance that attract iron or iron-like materials like cobalt, nickel, all these are iron-like substances which have some magnetic properties. So, any substance that attract iron or iron-like materials are called magnet. There are two types of magnet. One is natural magnet, another one is artificial magnet. Natural magnet are those magnets which are found in nature. Artificial magnet are those magnets which are made by man, like for example bar magnet, right? Horseshoe type magnet, compass needle is also an artificial magnet. Compass needle, all these are artificial magnet. Now, what are different properties of magnet? First of all, you know that suppose this is a rectangular shape bar magnet. It has two poles. One pole is called north pole, which are pointing in geographical south direction. Another pole is south pole, which are pointing in geographical north direction. When you suspend this magnet freely, what happens? It always points in north-south direction, right? So first properties of magnet is that it has two poles, north and south pole, and a freely suspended magnet always aligns in which direction? North-south direction. Magnet always aligns in north-south direction. North-north pole or south-south pole means like poles, and north-south poles are unlike poles. So if they are unlike poles, they always attract each other. Like poles, it means north pole, south pole. These are like poles. Like poles repel each other, while unlike poles means north south always attract each other. These are 1 or 2, 3 lines about magnet and their properties, right? Now after this magnet, you know, if any substance comes near this magnet, what happens? That substance experiences some force due to this magnet. It means something is present around this magnet. That something is called what? That something is called magnetic field, and that magnetic field is represented by magnetic field lines. So I will discuss next what do you mean by magnetic field, magnetic field lines, what are their properties. Then we come to this chapter, meaning of this chapter name, magnetic effects of electric current, which is explained by Oersted, right? So please take a screenshot of this one. Now next is magnetic field. What is this magnetic field? You know, if you put any substance near a magnet, what happens? That substance experiences some force. If you put, suppose one object is kept at this position far away from this magnet, right? Then this substance does not experience any force. If this substance comes closer to the magnet, again at this point, it does not experience any force. But if this substance, suppose it is kept at this point, now at this point, it experiences some force. Why? Because at this point, around this magnet, it has some property to exert force of attraction or repulsion on any object. And that property around this magnet is called magnetic field, right? This magnet, due to this magnetic field, any other substance experiences magnetic force due to this magnet. If there is no magnetic field, it does not experience any force. At this point, there is no magnetic field. At this point, there is no magnetic field. But at this point, near the magnet, there is some region or space around the magnet up to which any other substance experiences magnetic force. And that region around the magnet or space around the magnet up to which any substance experiences magnetic force is called magnetic field. It is space or region around a magnet where a magnetic force can be experienced, and it has both magnitude and direction. That's why it is a vector quantity. Now, how you represent this magnetic field around a magnet? With the help of this magnetic field lines. You can't see magnetic field lines. It is just an imaginary lines. Magnetic field lines are imaginary lines that graphically represents magnetic field around a magnet. To represent magnetic field around a magnet, magnetic field lines are used, and these are imaginary lines which represents magnetic field. There are some properties of this magnetic field lines, right? First one is, it is a closed and continuous curve. This magnetic field lines, it always forms closed loop. It is a closed and continuous curve, and it always originates from North Pole. It starts from North Pole and ends at South Pole, right? These are magnetic field lines. It starts from the North Pole and ends in South Pole outside the magnet. It starts from north and ends in south. It means north to south outside the magnet. But what is direction of field lines inside the magnet? Inside the magnet, direction is different. Inside the magnet, direction of field lines is from south to north. South to north, right? Inside the magnet. We must remember these points. Magnetic field lines originates from North Pole and ends in South Pole outside the magnet, and inside the magnet its direction is from south to north. Next important property is they do not intersect each other. Okay. These magnetic field lines represent magnetic field. If you want to find direction of magnetic field at this point, what happens? You draw one tangent at this point. This tangent gives direction of magnetic field. Now, if two field lines intersect each other, what happens? Suppose one magnetic field line is going like this one, another magnetic field line is going like this one. Now, at the point of intersection, you draw one tangent on this magnetic field line and one tangent over this magnetic field line. This tangent gives direction of magnetic field. So, at the point of intersection, there will be two direction of magnetic field because two tangents can be drawn, which is not possible. At one point, only one direction of magnetic field is there, right? So, magnetic field lines do not intersect each other because, you can write the reason, because what happens? At point of intersection, there will be two direction of magnetic field. Two direction of magnetic field, which is not possible, right? Which is not possible. That's why magnetic field lines never intersect each other. If you want to find direction of magnetic field, you just draw one tangent over that point. It gives direction of magnetic field. If you want to find direction of magnetic field at this point, you just draw one tangent at this point. You just draw one tangent at this. It gives direction of magnetic field at this point, right? Now, next property is, if the field lines are closer, then at that point field is very strong. And if the field lines are far apart, it means at that point field is very weak. It's clearly from this diagram that near the poles, field lines are very close to each other, right? They are very close to each other. It means field is strong at this point. As you move away from the pole, what happens? Field lines are separated from each other. It means at these points and at the middle of the magnet, field lines very separate from each other. That's why field is very strong. So closer the field lines, stronger the magnetic field. There is separation between the field lines. At that point, field is very weak. So these 2 points are very important. If the field lines are closer, then field is very strong, which is at the pole of the magnet. Here also North Pole and here also South Pole, field lines are very closer to each other. If the field lines are far apart, then field is very strong and it is most weak at the middle of the magnet. So these are some important properties of magnetic field lines. And what is this magnetic field lines? It is used to represent magnetic field. After this topic, I am coming to the main topic of this chapter, the magnetic effects of electric current. How, with the help of electric current, magnetic effect is produced. This is first half part of the chapter and it is explained by Orested. And the second half, reverse of this one is there. In that part, we discuss how this electric effect is produced with the help of magnetic field. So in that part, electromagnetic induction is there. There are 2 parts. In first part, how with the help of electric current magnetic effect is observed. Magnetic effect is observed. And the second half part, with the help of magnetic effect, electricity or electric current is produced. Right? So in this part, first I will discuss this part, first half part, then after the second half part, in which we'll discuss about electromagnetic induction. So please take a screenshot of this one, then move to the next topic. Okay, now Oersted observation. What is this? For many years, it was thought that electricity and magnetism both have no relationship with each other. But in 1820, there was one scientist whose name is Hans Christian Oersted. He observed that there exists relationship between electricity and magnetism. With the help of one experiment, he proved this one. He observed that when current, suppose there is a circuit, current carrying wire in which current is flowing. Now, if there is no current is flowing, then what happened? This is a magnetic compass needle. It does not show any deflection. This one is north and this one is south. It just points always in north-south direction, right? But he observed that when current flows through this circuit, what happens? This needle shows some deflection. Previously no current, needle is like this one. If current flows, needle deflects in this direction, right? And greater the current, more is the deflection produced in this magnetic compass. Now if the direction of this current is reversed, then the deflection also reversed, right? So this was observed by Oersted. First he observed that when current flows through a current carrying conductor or wire, magnetic needle deflects, and the more the current, higher the deflection. And if deflection direction of current is reversed, then direction of deflection also reverses. From this he concluded that this experiment shows that when electric current flows through a wire, it produces magnetic field around a wire. Why magnetic field? This needle only shows some deflection if it experiences a magnetic force, but here there was no magnet. So this current carrying wire or electric circuit behaves like a magnet, and around it magnetic field is present. If this magnetic field is present, then this needle deflects. It experiences a magnetic force. It means a current carrying wire behaves like a magnet, and due to this current carrying wire, this needle deflects. So first time Oersted, with the help of this experiment, proves that when electric current flows through a wire, it produces magnetic field around a wire. It means from this observation, he found that electricity and magnetism are very closely related. And also this phenomenon of generation of this magnetic effect with the help of this electric current, this is called magnetic effect of electric current. And this current carrying wire may be a straight wire, it may be a closed loop or circular wire, and it may be a solenoid. In all these three, this magnetic effect of electric current is observed. I will discuss all these three one by one. Hope it's clear to all of you. What is this Oersted observation? He observed that when current flows through a wire or any current carrying conductor, it shows some deflection. It means magnetic field is present around this current carrying conductor. And first time he find a relationship between electricity and magnetism. Both are very closely related. Hope it's clear to all of you. Please take a screenshot. Now, next topic is magnetic field due to a current carrying a straight conductor. We already discussed about Oersted observation. Oersted observed that when current flows through a current carrying conductor, there is a magnetic field around it. That current carrying conductor may be a straight line, maybe a circular coil, or maybe a solenoid. So first I am going to discuss about how magnetic field is produced due to a current carrying a straight conductor, right? To observe this one, you take one straight current carrying wire. Suppose this one is XY is a straight current carrying wire, and it is passed through the center of the cardboard. This one is cardboard, right? This straight current carrying conductor is passed through the center of the cardboard, and the ends of the conductor are connected to the battery through rheostat, ammeter and key, right? When no current flows through it, it does not observe anything. To observe magnetic field around this straight current conductor, what you have to do? You put some iron filings near the center of this straight current carrying conductor, right? Now, when no current flows through it, it is like this one. Now, when key is closed, it means current flows through this straight wire, right? Now, what happens when current flows through this straight wire? These iron filings arrange themselves in the form of concentric circles. With this straight wire is at the center of this concentric circles. These concentric circles are nothing but magnetic field lines due to these current carrying conductor, right? So, from this observation, it shows that there exists magnetic field around this straight current carrying conductor because iron filings arrange themselves in the form of concentric circles. It means there is some magnetic field around this straight current carrying conductor, right? And in the form of concentric circular field lines. This magnetic field is in the form of concentric circular field lines with conductor at the center, right? Now, if you increase the magnitude of the current, these magnetic field lines increases. It also depends upon the distance from the center of the distance from the conductor. Greater the distance, smaller the magnetic field. So, this magnitude of magnetic field depends on two factors. One is current. How it depends? Magnetic field is represented by capital V and it directly proportional to current passing through the straight current carrying wire. And also it depends upon distance from the conductor. It is inversely proportional to distance, square distance from the conductor. On these two factors, it depends. Greater the distance from the center of the conductor, what happens? Smaller the magnetic field. Smaller the distance from the conductor, greater the magnetic field. So, it depends on current and distance from the conductor. Now, if magnetic field is a vector quantity, it has both magnitude and direction. This is about magnitude. Now, how you find a direction of magnetic field which is produced near this straight current carrying conductor? For that one, there is one rule, give right hand thumb rule. According to this rule, what you have to do? You imagine that there is a straight conductor in your right hand. This is my right hand. Imagine a straight, suppose this is a straight conductor and this is in my right hand such that this thumb represents direction of current. This is the direction of current. Then you curl your finger. The direction in which the finger curls gives direction of magnetic field. If a current is flowing in upward direction, this thumb points upward and you just curl your fingers. This finger represents direction of magnetic field. Here it is in anti-clockwise direction. Right now, if current is upward, you curl your finger, that curls in the downward direction. If current is in downward direction. Now imagine this is straight conductor. This thumb represents direction of current. This is in downward direction. Curl your finger. Now it curls in the clockwise direction. So when the current is in downward direction, magnetic field is what? It is in clockwise direction. Right now, and when current is in upward direction, magnetic field is in anti-clockwise direction. So this is about magnetic field due to a current carrying straight conductor, right? Hope it's clear to all of you. Please take a screenshot fast. Now, next topic is magnetic field due to a current carrying circular coil, or you can say loop, right? Instead, observe that when current flows through a conductor or any wire, then around that wire, that conductor, magnetic field is present. Right? So, in case of a straight conductor, I already discussed. Next, circular coil. If current flows through any circular coil, then what happens? Magnetic field is present around that circular coil. It means magnetic field present means that circular coil behaves like a magnet. And if it is a magnet, it has north and south pole. How you find that one? Okay. So, suppose this is a circular coil, right? And in this coil, current is flowing in anti-clockwise direction like this one. This is three-dimensional figure, so I am drawn like this one. Suppose current enters through this and it moves in an anti-clockwise direction, right, like this one, and it comes out from the another end. So a current is flowing in anti-clockwise direction. Now how you find the direction of magnetic field lines? Okay, and magnetic field. So first you assume that each point of this circular coil acts as a straight conductor. First point is this one. Every point on the circular loop will act as a straight conductor. Now you know in case of a straight current carrying wire, how you find direction of magnetic field using right hand thumb rule. In the same way, also apply here. Each point, suppose I have taken this point, right? This point. Now current is flowing in anti-clockwise direction, it means in this direction, right? If current is flowing in this direction, then you curl your finger, it moves in like this one, in anti-clockwise direction. If you place your thumb in direction of current, assume that this is a straight conductor, right? This is a straight conductor. Current is flowing in this direction, like this one, right? Now you curl your finger, it moves in anti-clockwise direction, like this one, anti-clockwise direction. From one end, these magnetic field lines enters, another end, these magnetic field lines exits, right? Same way, at this point, at top of, when current is flowing in anti-clockwise, at this point, current is flowing in this direction, you assume this point, like this one. So if current is flowing in this direction, put your thumb in this direction, then curl your fingers, it curls in clockwise direction. So at this point, magnetic field is along this clockwise direction, and here anti-clockwise direction, right? So second point is magnetic field lines near the coil are nearly concentric and circular. Near the coil, it is concentric and circular rings. At every point, at this point also you find the direction of magnetic field. At this point also you find direction of magnetic field. So from this observation, it is observed that as you move away from the coil, what happened? This circular rings becomes larger and larger, and at the center, when you reach at the center of the coil, near this one circular ring is there, but when you reach away from this coil, at the center of it becomes a straight line. So at the center of this circular coil, these magnetic field lines becomes straight, and in this diagram you find that from all one end, from here, from the top surface, it is clockwise direction, here anti-clockwise. So from one end, these magnetic field lines enter, and from another end, these magnetic field lines exit, right now. So you know in case of bar magnet, from north pole, magnetic field line starts from the north pole and ends at south pole. In the same way here, you find that in one end, all the magnetic field lines enter, and from one end, all the field lines emerges, right now. So this face facing towards the coil, this, if current is flowing in anti-clockwise direction, then this face from one end, back surface, magnetic field lines enter, front surface, magnetic field lines emerges. So this front face acts as a north pole, because magnetic field lines starts from the north pole and enters or ends at the south pole. So the face which is facing towards you, it acts as a north pole, and back surface acts as a south pole, right? So as you move away from this coil, magnetic field lines becomes larger and larger, circular rings, and it becomes straight at the center. So at the center, the field lines are nearly straight, parallel, equidistant, so field is uniform at the center. Also, the magnetic field lines are in the same direction in the space enclosed by the coil. This is the space enclosed by the, so all the field lines enters from one end and ends at another end. So one end from where magnetic field lines emerges, this end acts like a north pole and back surface acts like a south pole in case of anti-clockwise current, right? As you move away from the center of the coil, what happens? As you move towards the center of the coil, the magnetic field lines increases, and at the center of the coil, the magnetic field is maximum, right? So these are some important points about magnetic field due to a circular current carrying coil, and how you find which, because magnetic field is present around this circular current carrying coil, so there it behaves like a bar magnet. So one end is north, another end is south. You can find from this diagram also. This face is north pole because magnetic field lines starts from north pole and ends at south pole. But how you find the direction of this magnetic field lines, right? And magnetic field. Direction of magnetic field is determined by using clock rule. According to this rule, looking at the face of the coil, if the current around that face is in anti-clockwise direction, then that face acts as a north pole. If current is flowing in anti-clockwise direction, looking at this face, then this face acts as a north pole. You like and this one, you write and like this one. So current is flowing in this direction, it means this face acts as a north pole. Now if you look at this face of the coil, if the current is flowing in clockwise direction, then this face acts as a south pole. If current is flowing in clockwise direction like this one, you write S like this one. So it is in clockwise direction. So you remember this clock rule. If current is in anti-clockwise direction, then that face is north pole. If current is in clockwise direction, then that face acts as a south pole. Right? Now, on which factors this magnitude of magnetic field depends? It depends on three factors. Number one is current. Greater the amount of current flows through this circular coil, greater is the magnetic field. Also depends upon radius of coil. If it is maximum at the center of the coil, magnetic field is maximum at center. If you move away from the center, field lines decreases. It means it is inversely proportional to radius of the coil, and on current it is directly proportional. And number of turns in the coil also it depends. So magnetic field is directly proportional to number of turns in the coil. Greater the number of turns in the coil, greater is the magnetic field. So B is directly proportional Ni by R. These are different factors on which magnetic field depends. So hope it's clear to all of you about this one. Magnetic field due to a circular current carrying coil. Take a screenshot of this fast. Our next topic is magnetic field due to a current carrying solenoid. In this one, what do you mean by this solenoid? Okay. First of all, you know that in case of current carrying circular coil, if you want to increase the magnitude of magnetic field, then you have to increase current and also number of turns in the circular coil. B is directly proportional to I, and B is also directly proportional to number of turns in the coil. So to create a strong magnetic field, you have to increase current. But if you increase more current, what happens? Overheating takes place. So there is some limit of current. You can't increase current above that limit. Okay. So the best way to increase magnetic field is what? To increase number of turns in the coil. And this can be used to make solenoid. What is solenoid? It is a coil of many circular insulated copper wire wrapped or wound closely in the form of helix. If you take insulated copper wire and wrapped in this form, in the form of helix, like a spiral binding, like, okay. So what happens? If you pass current through this number of turns, same current is flowing, but in different circular number of turns, different amount of magnetic field is present. So in this way, a strong magnetic field is present inside this solenoid. So this is solenoid. It is a coil of many circular insulated copper wire wrapped closely in the form of helix. This is helical shape. Suppose this is insulated copper wire and you wrap like this one. This is solenoid. And if current is flowing through this solenoid, what happens? Magnetic field is created inside the solenoid. It means it behaves like a bar magnet. This, when current is passed through, it behaves like a bar magnet. And if it behaves like a bar magnet, it means it has north pole and south pole, right? So how you find the direction? Which one is north pole? Which one is south pole? Okay. Here also you have to apply at different points. When you find the magnetic field lines, it is like this one. In one part, magnetic field current is flowing in downward direction. In another part, current is flowing in upward direction. Then again in one part downward direction, in one part upward direction. So using right hand thumb rule, you find the direction of magnetic field in half part and then in another half part. You find that magnetic field lines are like this one. In half part, it is like this clockwise direction. In another half part, it is in anti-clockwise direction. So in this way, you draw magnetic field lines and you find that the magnetic field lines enters, all these magnetic field lines enters from one end and emerges from another end, right? And at the center, these magnetic field lines are straight parallel lines. So from this diagram, it is found that, in case of bar magnet, suppose this is a south pole and this one is north pole. Now magnetic field lines are like this one in case of a bar magnet. Yes, no? It emerges, starts from north pole, right, and ends at south pole. Here also, it is similar to bar magnet magnetic field lines. Also here also, it enters through this end. It means this end behaves like a south pole, and it starts from this end. It means this end behaves like a north pole, right? So because in case of bar magnetic field line starts from north pole, so this end acts as a north pole, and here magnetic field line ends here at this pole, enters here, so this end acts as a south pole, right? So one end behaves as a north pole, and the end behaves as a south pole. If you draw a diagram like this one, the field lines inside the solenoid are in the form of parallel straight lines inside the solenoid. If there is a parallel straight lines, it means this represents uniform magnetic field inside the solenoid. Direction of magnetic field inside the solenoid is from south to north. Outside the solenoid, field is non-uniform. It is from north to south pole, so that it behaves like a bar. In this way, you explain magnetic field due to a current carrying solenoid. But there is one rule. You already studied about clock rule. You can easily find north pole and south pole. According to that rule, what happens? The end at which current is flowing in anti-clockwise direction, that end of the solenoid behaves as south pole. Here also, current is flowing like this one, then this one, and again this one, then this one. It means current is flowing in clockwise direction. So this end of the solenoid behaves like a south pole, right? So that's why another end behaves like a north pole. If you reverse the direction of current, if you change the positive terminal, negative terminal, then the current flows in this solenoid is in anti-clockwise direction. So from this side, if current is flowing in anti-clockwise direction, that is this end of the solenoid behaves as a north pole, and this end behaves as a south pole. In this way, you can easily find north pole and south pole with the help of clock rule. If current is flowing in clockwise direction, so this end of the solenoid behaves like a south pole, and other end behaves like a north pole. In this way, you explain magnetic field due to a current carrying solenoid. And this magnitude of magnetic field also depends upon current flowing through the solenoid, number of turns per unit length, and one important thing, nature of core material inside the solenoid. Which type of material is present inside the solenoid in which these insulated copper wires are wrapped. It also depends on that material. If depending upon the type of material which is present inside the core of the solenoid, it may be used as permanent magnet. It can be also used to make temporary magnet, or you can say electromagnet. So first, to take a screenshot of this one, then we'll discuss about electromagnet and permanent magnet. Okay, now when current flows through a solenoid, a large amount of magnetic field is created inside the solenoid, and that magnetic field is uniform also. Now, that property of solenoid is used to magnetize magnetic materials. How? Depending upon the type of materials placed inside the solenoid, it can be used to make electromagnets, or you can say temporary magnets, and also permanent magnets, right? So, how this electromagnet is formed, how this permanent magnet is formed? When these electromagnets are just solenoid, but what happened? Difference is what? With its binding on a soft iron core. If you take insulated copper wire and wind over a soft iron core, then it becomes electromagnets. Why? It is used to make temporary magnets using soft iron core, because soft iron has a property, it can be easily magnetized or demagnetized. When current flows through the solenoid, it is magnetized, when magnetic field is created inside the solenoid, and when current does not flow through the circuit, it can be easily demagnetized also. It means no electric field inside the solenoid. That's why soft iron core is used to make temporary magnets. In this one also, there is a north pole and south pole, because it behaves like a magnet. How you find north pole and south pole? Suppose this is a solenoid and insulated copper wire is like this one. Current is flowing like this one. It means in anti-clock, from this end A, it is flowing in anti-clockwise direction. And according to clock rule, anti-clockwise direction means this side north pole and that side south pole. If current is flowing through clockwise direction from this end A, right? Then this side becomes south pole and this side becomes north pole. In this way you can find easily north and south pole. So two lines you can write. A strong magnetic field inside solenoid is used to magnetize magnetic materials like soft iron core when placed inside it, because it can be easily magnetized and demagnetized. Where these electromagnets are used? They are used in electrical devices such as electric bell, electric fan, telegraph. In all these things, these temporary magnets are used. It is also used for lifting large masses of iron in case of crane also. Now next one is permanent magnets. How permanent magnet is formed? It is also just like a solenoid, but in place of soft iron core, inside the solenoid you put steel. It is just solenoid with its binding on steel. Why steel is used? Because steel has more retentivity than soft iron core. More retentivity means it can retain its magnetism even when no current flows through the solenoid. So it does not lose its magnetism easily because it has more retentivity than soft iron core. Then this is used to make permanent magnets. So these are two important properties of solenoid. Solenoid, magnetic field inside the solenoid can be used to make electromagnet as well as permanent magnet. Please take a screenshot of this one and move to the next topic. Next, force acting on a current carrying conductor in a magnetic field. Okay, Oersted observed that a current carrying conductor exerts force on a magnetic compass needle, and magnetic compass needle is a magnet, right? Now, Ampere suggested that a magnet also exerts force, equal and opposite force on a current carrying conductor. It means a current carrying conductor experiences a force when placed in a uniform magnetic field. Suppose external magnetic field is present from north to south direction. This is direction of magnetic field. Now this conductor enters inside, current carrying conductor enters inside this magnetic field. Then due to this external magnetic field, this current carrying conductor experiences a magnetic force, and the magnitude of magnetic force depends upon the magnitude of magnetic field, magnitude of current, and also length of the conductor. And one more thing, also angle between conductor and magnetic field. So this magnitude of force depends on current, length of conductor, magnetic field, and angle between conductor and magnetic field. It means force is directly proportional to BIL sine theta, where B is magnetic field, I is current, and its length of conductor, theta is angle between conductor and magnetic field. So from this one, it is clear that force is maximum when current is placed perpendicular to the magnetic field. It means this is the direction of magnetic field and this is direction of conductor through which current flows. If both are at 90 degree to each other, then it experiences maximum force. If both are in the same direction, it means force is minimum when conductor is placed parallel to magnetic field. That case theta is 0 and sine 0 is 0, and if it's perpendicular then sine 90 is 1, the maximum force is there. So it's clear that a current carrying conductor experiences force when placed in a uniform magnetic field, right? Now how you find the direction of that force? Its direction is given by Fleming's left hand rule. This is your left hand rule, right? Now stretch your thumb, this forefinger and this central finger. All three are mutually perpendicular to each other. Then this forefinger represents direction of magnetic field. This central finger represents direction of current. Then the direction in which the thumb present, it gives direction of force, or you can say motion of conductor. So if current is flowing in upward direction, right? So this central finger represents direction of current. You put this even in upward direction, and magnetic field is it from north to south. Then this is the direction of force in this case. Current is in upward direction, magnetic field is from north to south. Then this is the downward force is the direction of motion of conductor, right, or magnetic force. If the direction of current is reversed, it means if current is flowing in downward direction. So this is direction of current. It is flowing in downward direction. This is direction of magnetic field. Now in this case, motion of conductor or force experienced by the conductor in upward direction. This one. So direction of force is given by Fleming's left hand rule. According to that rule, you stretch your thumb forefinger and central finger of your left hand in such a way that all three are mutually perpendicular to each other. Then this forefinger, this is your thumb, this is your forefinger, this is your central finger, like this one. Okay, roughly I am drawing. So this forefinger represents direction of magnetic field B. This central finger represents direction of current. Then this thumb represents direction of force, or you can say motion of conductor. Right? This is Fleming's left hand rule. Hope it's clear to all of you. This central finger represents direction of current, forefinger represents direction of magnetic field, and this thumb represents direction of magnetic force, or you can say motion of conductor. This is Fleming's left hand rule and it is used to find direction of magnetic force. Right? Hope it's clear to all of you. Please take a screenshot of this one. Next, electric motor. You know, when a current carrying coil is placed in a magnetic field, it experiences force, and that principle is used to construct electric motor. So, electric motor is a rotating device which converts electrical energy into rotating. It rotates the motor into mechanical energy. And on which principle it lies? When a current carrying coil is placed in a magnetic field, it experiences force which rotates the coil. This force helps to rotate the coil. This is the basic principle of this electric motor. Now, there are different components of this electric motor. So, construction is, first one is armature. Armature or rectangular coil. This ABCD is an armature or rectangular coil. Armature. Right? So, first important component is armature or rectangular coil of insulated copper wire, and it is placed between two poles, north and south poles. Second is a split ring, and it is also called commutator. Commutator is a device which is used to reverse the direction of current. Here split ring acts as a commutator. It is used to reverse direction of current after every half cycle. This semicircular shape are two split rings which is used to reverse direction of current, and then carbon brushes. These two dark portion are B1 and B2 are carbon brushes, right? And these are attached to the two ends of the armature, and other points are connected to the battery. So current flows. Next one component is battery, and battery provides current to the circuit. Current flows through these brushes to the split rings in this armature. Right? Now what you have to do? You know, you have to apply Fleming's left hand rule. When current flows in one direction, these poles provides magnetic field in another direction, then it rotates this armature, ABCD rectangular coil, and in this way the motor rotates. So how it works? Okay, during first half cycle, right, current is flowing like this one, in this way, in upward direction. In AB, current is flowing in upward direction, and then in CD, current is flowing in downward direction. In AB, current is in upward direction, and CD, current is in downward direction, and field is from north to south. Right? Now you know you have to apply Fleming's left hand rule. If field is from north to south, this forefinger represents direction of field, and this current is in upward direction. This center finger represents direction of current, like this one. Then the force on this AB arm is acting in downward direction. This is the direction of force, and it is perpendicular to this plane. Right? Now in this AB, force is acting in downward direction. Now in this CD arm current is flowing in downward direction. It means current is in downward direction. This is direction of magnetic field. Then force is acting in upward. Right? So upward means inward and perpendicular to this plane. Downward means outward and perpendicular to this plane. So force on CD is acting in upward direction. Now what happens? Force on AB is acting in downward direction, CD is acting in upward direction. It means inward, and this force is outward. Now this coil rotates in anti-clockwise direction during first half cycle. Right? Now after first half cycle, during second half rotation, what happened? This slit rings changes their position. These are not fixed, only brushes are fixed. These are fixed, and current always flows through the brushes B1, B2. Now during other half rotation, R2 comes this side, R1 comes this side. It means AB and CD changes their position. Now this time current in CD arm is flowing in upward direction, and in AB arm current is flowing in downward direction. It means force on CD arm is acting in downward direction and force on AB arm is acting in upward direction. Again the coil rotates in anti-clockwise direction. In this way the coil completes one cycle in anti-clockwise direction with the help of what? With the help of split rings, because it helps in changing the direction of current, and so it helps in continuous rotation of coil by reversing the direction of current. In this way this armature ABCD continuously rotates in anti-clockwise direction, and this is the working of electric motor. Different examples of this electric motor are electric fan, mixer grinder, air conditioner, all these things. The working of electric motor is in the same way. So hope it's clear to all of you. Please take a screenshot of this one. Now, last topic of this chapter is electromagnetic induction. What is this electromagnetic induction? Okay, up to this topic, you studied how magnetic field is produced with the help of current carrying coil, right now? Now, reverse is also true. Here, you studied how electric current is produced with the help of magnet. And this phenomenon of inducing current in a coil by changing magnetic field is called electromagnetic induction, or you can write EMI, electromagnetic induction. The phenomenon of generation of electric current in a coil by changing magnetic field. And how magnetic field can be changed? Magnetic field can be changed when there is relative motion between coil and magnet. And it was first given by Michael Faraday. In his experiment, he showed that how when there is relative motion between coil and magnet, then magnetic field is changing, and due to that change in magnetic field, current is produced in a circuit. Okay, this one is first experiment. In this first experiment, there is one coil in which galvanometer is connected and there is one magnet. Suppose north pole is here or south pole is here, right? You know galvanometer? Galvanometer actually is a device which is used to detect the presence of current in a circuit. Actually, galvanometer is also used to measure a small amount of current, but the main use is it is used to detect the presence of current, whether current is flowing in a circuit or not. This is a galvanometer and there is one pointer. If the pointer is at 0, it means no current flows in the circuit. If pointer deflects in this direction or in this direction, it means current is flowing in a circuit. So here this galvanometer also shows some deflection when this magnet is moving towards this coil or away from the coil. This coil is stationary, right? Coil is stationary and this magnet is moving. When the magnet is moving towards the coil, what happens? Magnetic field lines are changing, it means magnetic field is changing, and due to that change in magnetic field, this galvanometer shows some deflection. Either the point moves in this direction or left or right. And if galvanometer shows some deflection, it means some current is flowing in this coil. Again, if the magnet is moving away from the coil, again galvanometer shows some deflection in opposite direction. So this experiment also shows that motion means there is a change in magnetic field around this coil, and due to change in magnetic field, current is flowing in this coil, right? Again, in another experiment, suppose this magnet is at rest, stationary, right? North pole and south pole, and suppose this coil is moving. This coil is moving. Now what happens when this coil is moving towards the magnet? Again, there is a change in magnetic field and this galvanometer shows some deflection. If the coil is moving away from the magnet, again this galvanometer shows some deflection. This experiment was performed by Michael Faraday, right? Now in the third one, suppose there are two coils. In one coil galvanometer is connected and another coil battery is connected. Battery is connected means current is flowing in one coil, and due to current in one coil, magnetic field is produced around it, and when this coil is moving towards this stationary coil, what happens? There is a change in magnetic field around this coil also, and this galvanometer shows some deflection. It means current is flowing in this coil also, right? So From these experiments, it is found that whenever there is relative motion between magnet and coil, current is produced in the circuit, right? So this phenomenon of inducing current in a coil by changing magnetic field is called electromagnetic induction. Now, how you find the direction of that induced current? This was given by Fleming's right hand thumb rule. Direction of force was given by Fleming's left hand thumb rule, and this direction of induced current was given by Fleming's right hand thumb rule. Here all the things are same. Here again this forefinger represents direction of magnetic field, right? This center finger, this thumb represents direction of motion of conductor. Then this central finger represents direction of motion of induced current. So stretch your thumb, this central finger and middle finger of your right hand in such a way that all three are mutually perpendicular to each other, right? Now this forefinger gives direction of magnetic field, this thumb gives motion of conductor, then this center finger gives direction of induced current in the circuit. This is Fleming's right hand rule. If this center finger represents, this forefinger represents direction of magnetic field, thumb represents motion of conductor, then this center finger represents direction of induced current. So hope it's clear to all of you. This is very, very important. This one is Fleming's right hand thumb rule. It is used to give direction of induced current. Now on the basis of this observation, there are two laws of Faraday, right? Faraday's first law and Faraday's second law. Faraday's first law is whenever there is relative motion between what? Coil and magnet, magnetic field changes, right? And due to that change in magnetic field, current or EMF is induced in the coil. And greater the change in magnetic field, greater the EMF or current produced in the circuit. This is second rule. Magnitude of induced current is directly proportional to rate of change of magnetic field lines induced with that coil. And change of magnetic field lines means it is also called magnetic flux. You studied about magnetic flux in class 12. So this magnitude of induced current directly proportional to rate of change of magnetic field lines. Greater the change in magnetic field, greater the current produced in the circuit. This is Faraday's first law and second law. So this was all about electromagnetic induction. Hope it's clear to all of you. Please take a screenshot of this one. So with this, I am going to end my class. Hope you like this one short revision of chapter electricity. If you liked it, then don't forget to subscribe my channel. Okay students, keep revising and stay tuned with this channel. Thank you.